Today, we are going to break down a concept that honestly powers almost every single piece of software you use. It's called object-oriented programming, or OOP for short. It's a huge topic, so let's just dive right in. So, have you ever stopped to think about this? How do engineers build something like a giant social media platform or a modern video game? We're talking systems with millions of lines of code, and keep it all from just falling apart. Well, the answer lies in this really powerful shift in thinking. Instead of just writing a super long to-do list for the computer, they actually modeled the real world directly in the code. And that is the core idea behind OOP.
Okay, so let's put a pin in that and get a bit more formal. What exactly is object-oriented programming? We'll start with the big picture idea before we get into all the nitty-gritty details.
All right, here's the definition you'd see on an exam. OOP is a way of designing software by creating a collection of interacting objects. And here's the key. Each object bundles together its own data, what we call its state, and the things it can do, which we call its behavior.
So why do we even bother with all this? Why does it matter? Because for big, complicated projects, this approach is an absolute game changer. It takes all that complexity and tames it. It makes code way easier to fix and update, and it lets you reuse pieces instead of writing the same thing over and over. Trust me, it's a cornerstone of modern software for a very good reason. Okay, so if OOP is all about these objects, where do they actually come from? Well, it all boils down to two fundamental building blocks. I want you to think about it like a blueprint and the actual building you construct from that blueprint. First, you have the class. A class is the blueprint. It's super important to remember that it's not a thing itself, it's the design for a thing. It lays out all the properties and all the capabilities that anything made from it is going to have. And then, from that blueprint, you create objects. An object is the actual building. It's a real, living, breathing thing inside your program, and it's created from that class template. And every single object has its own unique data and its own identity. Let's make this really concrete, okay? A bank account class is the blueprint. It defines that every bank account will have an account number and a balance. But your specific account, with your unique account number and your specific balance, that is an object. See the difference? Now we get to the really good stuff. This is the absolute core of OOP. These are the four fundamental principles. You can think of them as the pillars or even superpowers that give this whole paradigm its power. If you can get your head around these four, you really understand OOP. First up is abstraction. This one is all about simplicity. It's the idea of hiding all the messy, complex inner workings of an object and only showing the essential controls. We're focused on what an object does, not getting bogged down in how it does it. You know, the best analogy is driving a car. You only need the steering wheel, the gas, and the brake, right? You don't need to be a mechanic and understand the engine schematics just to drive to the store. All that complexity is hidden from you. It's been abstracted away. Our second pillar is encapsulation, and this one is all about protection. If abstraction is about simplicity, encapsulation is like building a protective bubble, or a capsule, around an object's data. You bundle the data and the tools that work on that data together, and you stop anything from the outside from messing with the data directly. So how does that actually work? Well, the object's data is marked as private, kind of like treasure locked away in a chest. If another part of your program wants to see or change that data, it has to ask nicely through a specific controlled doorway. This creates a secure barrier that prevents all sorts of bugs and accidental changes. It's a lifesaver. Okay, everybody lean in for this one, because this is probably the most common point of confusion, and I guarantee it's a favorite exam question. Abstraction and encapsulation. They sound kind of similar, but they're solving two very different problems. Here's the key difference. Let's break it down. Abstraction hides complexity to make something easier to use. It's all about the design. Encapsulation, on the other hand, hides data to protect it. That's all about the implementation. So a simple way to remember it, abstraction hides the messy how, while encapsulation hides the precious what. All right, our third pillar is inheritance, and this is the superpower of reusability. It's a cool mechanism that lets you create a new class that's basically a more specific version of a class you already have. This new child class automatically gets or inherits all the features of the parent class. The easiest way to think about this is just with the phrase is-a. It's an is-a relationship. A car is a vehicle, so you could create a general vehicle class with things like speed, and then have a car class inherit all of that, and then add its own special things, like how many doors it has.
And that brings us to our fourth and final pillar, polymorphism. I know, it's a bit of a mouthful. It literally means many forms, and it is a seriously powerful idea. It means you can have lots of different kinds of objects that all respond to the exact same command, but each one responds in its own special way. For instance, imagine you have a bunch of different shape objects. You've got circles, squares, triangles, whatever. You can just tell every single shape in your list to draw itself. The circle object knows how to draw a circle. The rectangle object knows how to draw a rectangle. It's one single command, but you get many different results. That, right there, is polymorphism. So we have our building blocks, our classes and objects, and we have our guiding principles, the 4 pillars. But objects don't exist in a vacuum, right? They interact with each other. And understanding how they relate is really the final piece of the puzzle. There are 3 main types you need to know. First, you've got association, which is just a loose link. Think of a teacher and a student. They're associated, but they can totally exist without each other. Next is aggregation, which is a weak has-a relationship. A department has lecturers, but if the department shuts down, the lecturers don't disappear. They still exist. And finally, there's composition. This is a strong has-a link. A house has rooms. If you demolish the house, the rooms go with it. They can't exist on their own. And here is a golden nugget of wisdom, a real examiner favorite. In professional software design, you should almost always favor composition over inheritance. And why is that? Well, because building objects out of smaller independent parts, that's composition, is way more flexible than locking them into a rigid family tree like you do with inheritance. So, as we wrap all of this up, I want to leave you with a final thought to chew on. We've gone through the rules, the pillars, the relationships, but is object-oriented programming just a technical checklist for programmers? Or is it a fundamentally different, more powerful way of thinking about how to break down any complex problem into small, understandable pieces? It's that shift in thinking that truly separates the good programmers from the great ones.